folks at home? Well, couple things. Let me grab some packets. For those of you who are all virtual, Unit 4 is right here. And I would like for you to come in and grab one of these either today after school or tomorrow all day. Tomorrow all day is pickup. And I think tonight they're staying here till like 7 o'clock or something like that. So either in the next, I guess, 5 hours, you can come to Wausau West and pick one of these up downstairs. I'll have them on the table down below. Or you can pick one up tomorrow sometime during the day. If you're a B student, you're going to be here next week and I can give you one. That's perfectly fine. And if you're an A student, you're in front of my face and you have one. Excellent. Cool. So today we are going to finish up 313. We are going to start into our in-class review, which is actually pretty big, and then we'll call it a day. Okay. Tomorrow I have a chromatography lab for you. It will be pretty short and pretty simple. So fear not. It's been a long time since I've given you any lavish things on Friday. Tomorrow's lab will be very, very simple. I would anticipate a half hour's worth of engagement. Okay. Next week, Monday, we will have an in-class review again. We will keep plowing through the in-class sheet. And next week, Tuesday, we will have our Unit 3 test on its learning. Okay. The answer key to all of those things will be posted. I kind of want to wait until this weekend. Maybe I'll post it tomorrow, actually, is what I'll do. I think that's the best appropriate time, just to make sure if anyone wants to study this weekend. I will post the answer keys to the in-class review. I will post the answer key to the other review sheet on there, because, again, every single unit, you got 2 review sheets to stare at. Yeah, and I'll post all the answer keys to the homework assignments as well. And you should be good to go and plenty to look at in terms of studying for next week, Tuesday. Yeah. I don't think I have any other announcements. I don't think so. All right, let's finish up 313, the Beer-Lambert Law stuff. We left off with this graph. And if you were in the first hour yesterday, or if you watched the online video, we were struggling with the scale on the x-axis. I've streamlined the process and made life much simpler. So here's the deal. We're going to assume that every single number on the x-axis is times 10 to the negative 3. And then I numbered it 1 through 15, skipping every other line. So essentially every line is 0.0005. Okay, 5 times 10 to the negative 4th. But it brains like whole numbers much better than we do scientific notation, and much better than we do decimals. So I think this is a nice, easy way to do this, where I'm just saying the whole darn scale here for the x-axis is 10 to the negative 3, and then I'm just listing 1 through 15. So really, when I go back up to the numbers up here, what I'm saying is this is like 1, 2, 5, 8, 10, 13 in terms of that scale, right? So it'll fill it out very, very nicely. So to start class, you have data. You have a graph with appropriate labeled axes. Try to plot those points if you could, and we'll draw our graph. Go for it. And I'll try to do the same. All right, I tried my best. Hopefully you got somewhere close to that. And now we gotta connect the dots here. This is gonna end up poorly. Yep, pretty poor. That was worse than last hour. That's a line, obviously, as it wheels its way through. That's a line, kind of. But we have a linear relationship between the absorbance and the concentration of the data that I've provided you. Okay? Now, let's revisit what the heck this whole thing is all about. So this data was in relation to the Beer-Lambert Law, this equation. Okay? What we had done is we have graphed the absorbance, Y, versus concentration, X. And the other chunk of this is M. That's the slope. Well, we have a linear plot now, right? So let's revisit yesterday. Do you remember what B was? It's the path length, and the length of that would be 1 centimeter. So long story short, the slope of this graph, the slope of our data, is going to be the molar absorptivity, that little lowercase epsilon. Okay? I said yesterday that we could only solve for this value through data, and that's true. We can't just look up this value in a book because it depends upon the type of chemical you are testing, and it also depends upon the wavelength of light that you're using in that instrument. It's very specific for the instance or the circumstance that you set the experiment up as. So long story short, the only way you can solve for a little epsilon, or the molar absorptivity, is by doing this, making a graph from data and finding the slope. So let's do that. We now have data for the concentration and absorbance of this experiment using Beer-Lambert Law. We can solve for the slope. How do we get the slope from our data and our graph? How can I get that?
Rise over run.
Yes, he's right. The rise over the run. In other words, the change in Y divided by the change in X. Good old-fashioned slope finding. Let's do that. We still are using this equation eventually, okay? And what we want is the slope. The slope, we know, equals our change in Y over our change in X. Let's use our data. What values are my Y values again? Absorbance. Now, when I find the slope, or my change in Y, what data points should I pick?
Top and the bottom.
Let's pick the top and the bottom. Why would I want to pick the two data points furthest away from one another? You're encompassing the entire set of data, right? If I use the first and last data point, I'm finding the slope of this whole range as opposed to finding the slope of like that little snippet. You know what I mean? So yes, absolutely. Now, in theory, this should be linear, right? In theory, the slope should be the same throughout. But if we're in an actual lab and we collected actual data, spoiler alert, you're not going to get perfect linear data. Will it be close? Yeah, probably. Should it be pretty darn linear? I hope so. But in a real setting, we would want to encompass as much of the data as possible when solving for slope. So let's use the first and the last data points to find our slope. Yes, Sam?
What if the last data point is an outlier? Then that means that we'd have to run like an algorithm that just finds the line of regression. Or no, not even an algorithm. Use the regression formula. Why don't we use the regression formula instead for more like reliable slope finding tools?
Now, here's the truth of it. You're right, but I would rather let a computer do all that nonsense than, do it by hand. So yes, if we were in Excel or Google Sheets or whatever people Desmos or whatever you guys use for your graphing capabilities, yeah, we would let the computer do all of its magic. But since we're doing this by paper, let's make life moderately simple and let's use our change in y over change in x for today. All right, so my slope equals change in y over change in x. Somebody want to give me those numbers? What's the biggest number? 1.6 something.
686.
Thank you. Minus
0.166.
Awesome. And for x, what's the largest value of our concentration?
1.344 times 10 to the negative 2.
Minus, I think it's this, isn't it?
Yep.
All right, cool. And we can punch that in. And when you do that, what do we get for our value of slope? That means it's calculator time. I'm going to time my shoe. What do we get?
125.82.
Awesome. I'm going to switch that to 3 sig figs. 126. Now, what's the label of this thing? Ooh.
Centimeters, liters divided by moles.
You're close? You are close. Let's go through it. Absorbance. Does anyone know the label or unit of absorbance? Trick question. There isn't one. It is a unitless value. It's essentially a ratio of how much light what there was and how much light passed through, right? We're checking how much light is absorbed. So it's truly just a ratio of the intensity of light in the beginning and the intensity of the light afterwards. So there's no label. So absorbance, I'm going to set this up kind of like this, okay? Where I have like my factors, and this is A, E, B, C. And I'm just going to use labels in here or units in here, if that makes sense. Okay, this is labelless, has no unit. On the other side, what's the unit or label of C? What is C? Concentration. What label do we use, or what unit is that? Molarity. Moles per liter. Big M. What's the unit or label of path length? Centimeters. Now, I want the left-hand side of my equation to have the same unit as the right-hand side of my equation, right? So if this is completely unitless, what units does my molar absorptivity need to have?
1 over centimeters per meter. Or no, times molarity.
Yeah, I knew what you meant. 1 over centimeters times molarity. Sorry for getting tiny there. But that's the label of molar absorptivity. That is, it's the absolute correct label of molar absorptivity. So I'm going to write this as Cm to the minus 1 times molarity to the minus 1. Okay, because again, when you raise something to the minus 1 power, right, that just means it's in the denominator. Okay. So this is molar absorptivity from our slope, from our graph, from our data. Now, how can we use that? For what purpose does it serve? Here's what that does for us. Once we've collected a data set using the Beer-Lambert law, and we plot this graph, we find the slope. Now, what we can do is we can solve for the molarity of an unknown substance. So now, this person in this hypothetical experiment takes a sample of another solution, a solution that they don't know the molarity of, some unknown sample. They put it in the spectrophotometer, which is that instrument that we're using in this lab, and they check for the absorbance. They find that the absorbance is 0.888. Now we can solve for the molarity of that unknown by using Beer-Lambert law. Here's our equation. We just were given absorbance in the problem. We just solved for the molar absorptivity 2 seconds ago on the previous problem from our slope. The slope from our graph was 126. And that, again, is centimeters to the negative 1 power times molarity to the negative 1 power. And then we multiply that by the path length. What's the path length? 1 centimeter, multiplied by the concentration, which is what we don't know, which is what we're trying to solve for. Solve for the molarity if you could, please. I'll do the same. And spoiler alert, 126 times 1 is absolutely 126. I did that in my head. I know you're impressed. I've got lots of degrees and been teaching for a while. I am getting 7.05 times 10 to the negative 3 molar. Anyone want to confirm? Sweet. Okay, so now, just for the sake of argument, okay, because this is the first time we've ever looked at Beer-Lambert stuff, and there will be a video next week, Friday, for a Beer-Lambert actual experiment with real data that I collect for you, okay? Let's just go back. Here's my unknown. Let's look at the actual data set that I gave you originally. What was the absorbance of our unknown from that problem, that last problem we just did? 0.888. It kind of falls between these two data points, right? And what did we solve mathematically for the molarity of that stuff? 7.05 times 10 to the negative 3, which falls right between those two. It makes sense, right? We can kind of double check just to make sure we mathematically did algebra correctly. And the unknown had an absorbance between these two, and the molarity ended up being between those two. Good, that makes perfect sense. That's where they both should fall because it's a linear relationship, right? As absorbance goes up, we found concentration went up. So when we test an unknown sample using the slope from our graph, we should absolutely have both the concentration and the absorbance fall between the same data points. Okay? Cool. That's all I have on 313. For those of you at home, what we're going to do for the rest of the hour is we're going to start the in-class review. I don't think it serves much purpose for you to hang out in the digital classroom unless you want to. But essentially, we're going to be working on the in-class review, and I'll post the answer key to that tomorrow. So you can leave the meet if you'd like to and get started on the in-class review and start chipping away at some of those problems and getting ready for next Tuesday's test. Have a lovely day.